Let's tackle example 5. Now, to start off, we need to find all of our things. We start with the domain. Domain comes from the denominator. So let's go back and factor the denominator. So this is my easy kind of factoring. I just need to multiply to 2 and add to 3. So that's a positive 2 and a positive 1. So my domain, x plus 2 cannot equal 0, x plus 1 cannot equal 0. So x cannot be negative 2, and x cannot be negative 1. So now I can write my domain out. Next, we always find our wholes next. Now, to find the wholes, I need to factor the top and the bottom to see if anything cancels. Now, you might be looking at that numerator thinking, how on earth do I factor that? Well, you did that last chapter. The way we factor that numerator is with synthetic division. So I'm going to take my numerator down here. And I'm going to do synthetic division to fully factor this. So here's what I would like you to do. You should remember how to do this. We need to list our possibilities here, test out those possibilities, find the one that gives us a remainder of 0, write our multiplication statement out here, and then factor the quadratic. So I would like you to pause the video, try to do this on your own first, and then come back to see how you did. I told you this problem has everything. So I got my factors of my constant, divided my factors of my leading coefficient to give me my possibilities of plus and minus 1 and plus and minus 1/2. I tried them until I got negative 1 to work. Got a remainder of 0. 0 of negative 1 means x plus 1 is the factor, and this is what I had left over. So then I just needed to factor that. So I did first times the last, got 2, exchanged the 3 for the 1 and the 2, and then found what the first 2 had in common and the last 2 had in common to get it all the way factored out. And I noticed I had x plus 1 twice, so that gives me x plus 1 squared and 2x plus 1. So now I can come back here. I now have this numerator all factored as x plus 1 squared, 2x plus 1. So now I can check for wholes. I have everything factored. Let's see if anything on top and bottom cancels. And looky there, I have an x plus 1 on top. Well, I have 2 of them on top actually, and an x plus 1 on bottom. So I'm going to cancel the one x plus 1 on bottom with one of the x plus 1s on top. So I'm left with an x plus 1 on top and a 2x plus 1 on top and an x plus 2 on bottom. So that is my simplified version after I canceled stuff out. So to find my whole, I take what I canceled out, set it equal to 0. So it looks like the x value of my whole is going to be at negative 1. To find the y value, I plug that into my simplified version. And it looks like I get a 0 times a, let's see, 2 times negative 1 is negative 2 plus 1 is negative 1. All over negative 1 plus 2 is a 1, which equals 0 times negative 1 is 0 over 1, which is 0. So my whole is going to be at negative 1 comma 0. So let's graph that. Open circle at negative 1 comma 0. Now look at this. This whole happens to also be an x-intercept. Now we know that anytime we have an x-intercept, we need to do even and odd. So even though this is a whole, because it happens to be on the x-axis, we do also need to do even or odd. So I look at what I canceled, the x plus 1. The exponent on that x plus 1 was a secret 1, which is odd. So this x-intercept whole is odd. Now let's find my x-intercepts. For the rest of the problem, I need to use my simplified version. So x-intercepts, let's look at the numerator of my simplified version. I get x equals -1 and x equals -1/2. So I have -1, 0 and -1/2, 0. However, you'll notice that -1, 0 we already used as a whole. So this is actually what we call a fake x-intercept. This is not an x-intercept, it is actually a whole. However, this is still an x-intercept. And we know it's an odd one because of the exponent of the secret 1. So I'm going to come right here at -1/2, 0. It's getting kind of squishy. This is also an odd x-intercept. And now I can move on to y-intercepts. Plug in 0. So I get 0 plus 1, 2 times 0 plus 1, and 0 plus 2. 0 plus 1 is 1. 2 times 0 plus 1 is 1. 0 plus 2 is 2. That gives me 1/2. So I have a y-intercept right here at 1/2. Vertical asymptotes, look at the denominator of the simplified. So x plus 2 equals 0 gives me a vertical asymptote at -2, which is also odd due to the secret 1 exponent on that factor. So I can do a vertical asymptote right here at -2. Do a little O so I remember it's an odd one. And last step, finally, we do our end behavior. Look at our simplified version. We need to look at the degree on top and bottom. So my simplified version, I have an x plus 1 and a 2x plus 1, and then an x plus 2. This is in factored form, which means to find the degree, I need to get rid of all of the constants. Basically, just keep your leading terms of each factor and multiply those together. So this gives me 2x squared on top and an x on bottom. So this is a degree of 2 on top, that exponent of 2, and a degree 1 on bottom. So this is top heavy, which means I need to do my long division. So we're going to take this, we had it in factored form. I want it in all foiled out in standard form so that I can actually divide it. So I need to foil these two things together, meaning these two things together, which I actually already did. X plus 1 and 2x plus 1. That is these two, which means foiled together is going to be that. So I have 2x squared plus 3x plus 1. Let's write this down. 2x squared plus 3x plus 1 divided by my denominator of x plus 2. And I need to do long division on this because I'm top heavy. So x times what is 2x squared? That's a 2x distributed out. Change the signs. And I get -1x, bring down the 1. X times what is -1x? That's a -1. Distributed out. Change the signs. And I get a remainder of 3. However, I don't really care what the remainder is. I just care about this. I do y equals 2x minus 1, which is my quotient. And there's my end behavior. See? I told you this problem has everything in it. So we're going to graph this as mx plus b. I have a y-intercept at -1, and then slope of up 2 over 1. Phew! And that tells me where to put my stars. I finally have everything here. Let's graph this. So to start off with, I know I need to go through my y-intercept. To the right of the y-intercept, there's nothing between it and my star, so just point to the star. To the left, the next thing I have, let's zoom in on here, there's a lot going on, so you can see a little better, is this x-intercept. This is an odd x-intercept, so I cross through it. The next thing I have is this hole, which is also an x-intercept, so I'm going to circle back around to it. It is an odd x-intercept, so I cross through it. Now I have this asymptote. I can't go down, or that would make another x-intercept, so I've got to go up. And it's odd, so if I'm up on one side, I'm down on the other side. And then there's nothing between this and my star, so I curve around to point to my star. And that right there is the hardest rational function that you should ever be asked to graph, but it really, really does have everything in it. And that is all for graphing rational functions. In 3.4, we're going to move away from graphing and talk about sine arrays. See you then.